Okay, ladies and gentlemen, let's start with lecture 12. Lecture 12 is paragraph 4.4 in the textbook, 4.3 in the textbook, which is transient heat conduction in semi-infinite solids. This chapter is about transient heat conduction. It is how temperatures changes as a function of time, and it consists out of 4 parts. The first one was the lump system approach. The second one was transient heat conduction in large plane walls, long cylinders and spheres. Then transient heat conduction in semi-infinite solids. We've done that with the previous lecture, and we are going to finish that today. And then with the next lecture tomorrow, we're going to do paragraph 4.4, which is transient heat conduction in multidimensional systems. Okay. Semi-infinite solids. What are semi-infinite solids? Well, normally we would think of it as big bodies. For example, the Earth is a good example of a semi-infinite solid. And we've looked at the example where the Earth was exposed to snow or ice at minus 15 degrees Celsius. And we saw that it takes about 3 months before the Earth would freeze at a temperature of 800 millimeters from the surface. So that is the first good example of a semi-infinite body. A second good example would be the Moon, which is also a very big body. But except for those, you might think, well, there's not a lot of applications for semi-infinite bodies. Well, there is. Large plane walls, for example, can also be approximated as a semi-infinite body, and many other bodies. For example, your own body can also be approximated as a semi-infinite body if you're interested in the temperature changes very close to the surface. So any body where you just want to see how the temperature changes very close to the surface can be approximated as a semi-infinite body. Okay, so now let's look at if we have 2 semi-infinite bodies that makes contact with each other. Okay. This semi-infinite body is at a temperature TA. So this is body A and this is body B, and both of them are at different initial temperatures, TAI and TBI. And this body will have a certain thermal conductivity, which is A, a certain density, which is also A, and a certain CP value, which is also CPA. And this one will have different values. So that would be the thermal conductivity, its density, and its CP value. So 2 different bodies, and they make contact with each other. Now, before we go on with that, I want to ask you to touch the wooden bench in front of you. Okay. Now, if you can, try to touch a piece of steel there underneath your bench. Which one is the coldest? Who thinks that the steel is the coldest? Okay, let me see. And the bench? And anybody that disagrees? Okay, quite a number of them. Why do you disagree?
It's exactly the same temperature.
They are at exactly the same temperature. Okay. They are exactly at the same temperature. If you would take a thermocouple, if you would take the surface of the bench, you would put a thermocouple on top of it, and you put some insulation material over it, and you go and measure the 2 temperatures, you would see that they are exactly at the same temperature. Now, why does the one feel colder than that of the other? Normally, it wouldn't really bother us, except in winter. In winter, when you get out of your bed, then you would feel it's a little bit cold. Okay. And many people will say, well, let's put in a carpet, okay, because then it is not so cold. Now, unfortunately, if you go and take measurements, you would see that the carpet temperature would be exactly the same temperature than that of the tiles in the house. Or even if you put copper floors in, it would also be at the same temperature. But your experience when you measure with your finger or with your feet is going to be different. And let's see what is the explanation of that. And the explanation we can do with starting to say, well, let's consider these two bodies. And if we plot the temperatures of these two bodies, then this body is at the temperature TA. Okay? And this body is at the temperature TB. Obviously, we can also switch it around if we want to. Okay. But if these two bodies make contact with each other, we know that if there is a temperature difference, then the heat is going to flow from the one body to the other body, and the heat flux of the one must be equal to the heat flux of the other. Because there's no other place where the heat can go to. So the heat transfer is from body A to body B. And what we now can say is that the heat flux on the surface of A is equal to the heat flux on the surface of B. And with the previous lecture, we've seen that the heat flux can be written as K multiplied by Ts minus Ti divided by the square root of pi multiplied by alpha T is equal to, but we have to distinguish it from the right-hand side where this K would be the thermal conductivity of body A. This temperature is going to be the initial temperature of body A, and this is also going to be the alpha of A, which is then equal to the thermal conductivity of B multiplied by Ts minus Tbi divided by the square root of pi multiplied by alpha multiplied by time T. And we know that alpha is the thermal diffusivity, and that is equal to K divided by rho C. Okay. Now if we look at this problem, okay, at 1 second, okay, then the 1 second of body A is equal to the 1 second of body B. Do you agree? Okay, because time equals 0, we put them together. So 1 second later, this time is equal to that time. And 5 seconds later, it is exactly the same thing. The two time terms are exactly the same. So in this equation, we can cancel those two terms. Solution is not going to be a function of time. Okay. And for convenience, we are going to look at this term, which is equal to the square root of K multiplied by rho multiplied by Cp, and I'm going to write that as a constant which is equal to F. So we see that if we take away the time, the pi's obviously cancel. We write the alpha as equal to K divided by rho C, and we solve the temperature in this equation. Okay, then we can write that the surface temperature is equal to Fa multiplied by the initial temperature of body A plus Fb multiplied by the initial temperature of body B divided by Fa plus Fb. Okay. So the surface temperature is being determined by the initial temperatures and the values of FA and FB. So if we now go and plot the temperature distribution of the surface as a function of time, then we will see at t equal 1 second that the temperature distribution is going to look something like that. So that is equal to t equal 1 second. And if it is 5 seconds, what is the temperature then going to be? Temperature after 5 seconds is going to be exactly the same. So we see that the surface temperature is not a function of time, okay, because the time disappeared. Okay. So it means that after 5 seconds, the solution might look like that. Okay. And after 60 seconds, something like that. But all of them goes through that one point, Ts, the surface temperature. It's not a function of time. Okay, 2 observations that we can make from this equation. The first observation is that if Fa is equal to Fb, what does that mean? Fa is equal to Fb, it means that this body and this body are made from the same material. If they are from the same material, then all these properties would be exactly the same. So Fa is equal to Fb, which means 2 bodies of the same material. Then it would mean that the surface temperature would be equal to the initial temperature of A plus the initial temperature of B divided by 2. Okay. Let's just check it. Let's suppose Fa is equal to Fb is equal to 3. Okay. Then the surface temperature would be equal to 3 times the temperature, initial temperature of A, plus 3 times the initial temperature of B, divided by 3 plus 3, which is equal to 3 times the initial temperature of A plus the initial temperature of B divided by 6, which is equal to the average temperature. That's the simple case. First observation. The second one is that the surface temperature will be dominated by the largest F. Dominated by the largest F. Surface temperature is being dominated by the body with the largest F value. And let's show that with an example. An example is, it's winter, okay? It's winter, and you get out of bed, and your 2 feet touches the surface next to your bed. Okay. You will be body A. Okay. Body B is going to be a tile floor. Tiles is body B, and its temperature is going to be 15 degrees Celsius. So it's not really that cold. Okay, 15 degrees Celsius. So that's the first scenario. And then you decide, no, this is too cold. I'm going to put a carpet in my bedroom. Scenario 2 is carpet. Again, that is going to be body A. This is now going to be body B. And After you've put in the carpet and you take measurements, you're going to see that the temperature measurement of the carpet shows that it is also going to be 15 degrees Celsius. And the room next to yours is still in tiles and still 15 degrees Celsius. Okay, the next one, some of your mates decided, no wait, they want to really wake you up, and they put a copper plate next to your bed. Okay, again, that is going to be body A, that is going to be body B, and the copper plate is also going to be at 15 degrees Celsius. In all three cases, we would also like to know what is going to be the heat flux. What is the heat flux going to be between you and the surface? Okay. Now, you're this human being, so if you're not sick, your temperature should be 37 degrees Celsius. We know that 72% of your body is water, so we've done it previously where we've determined the thermal conductivity, which is then equal to 0.623 watts per meter Kelvin. The density, which is equal to 996 kilograms per cubic meters. And Cp, which is equal to 4.178. Take note, kilojoules per kilogram Kelvin. And if your feet are about the same size as mine, then the surface area of one of your feet should be about 0.020 square meters. And the surface area of your body, the total surface area on the outside, is approximately 2 square meters. Okay. And we're also going to look at the example where you're going to jump into a pool of water at 15 degrees Celsius. Okay, so these are the three typical scenarios. Okay, this first scenario is in terms of properties, human flesh, HF, human flesh. Okay, now for human flesh, the K, the thermal conductivity, although we've written it there, I want to put everything here together in one table so that we can see exactly what is going on. So for human flesh, the thermal conductivity is equal to 0.623. Okay, the density, kilograms per cubic meters, is equal to 996. The Cp value, now in joules per kilogram Kelvin. Okay, that value is in kilojoules per kilogram Kelvin, so it is equal to 4178. And we're going to calculate the F value, the surface temperature, the heat flux, and the total heat transfer. The heat flux in watts per square meter and the total heat transfer rate in watts. So everything in one table. Okay, so those are the properties for human flesh. The properties for the tiles, if you go and look in your textbook, you'll see the thermal conductivity of tiles is equal to 1.34, which is very close to that of cement, 1.34. The density, 1920. The Cp value, 790. Then for a carpet, it is equal to 0.039, 1121, and 1420. And for the copper, it is 401, so it is a very good conductor of heat. The density is 8933. The CP value is 385. And those are the properties for the 4 different bodies that we're going to consider. Okay. You've got all the properties? Are you still writing? Anybody? Okay, I'm going to give you a minute. Human flesh 0.623, 996 and 4178. Tiles 1.34, density 1920 and CP 790. The carpet 0.039, the density 1120, CP 1420, the copper 401, density 8933, and CP is equal to 385. Okay. So if you look at this, you would say that to keep the cold out, I actually would prefer the carpet, isn't it? Because the thermal conductivity is the lowest. It is a good insulator against the cold. Good insulator. Let's see if that is the case. Okay. Let's look at the first possibility, and that is human flesh and the tiles. So you get out of the bed and you step onto the tiles. Then the surface temperature is going to be the F value of the human flesh multiplied by the initial temperature of the human flesh plus FB, which is the properties of the tiles multiplied by the initial temperature of the tiles divided by FA plus FB. Okay. So we see that to do the calculation we need the properties F. Okay. F is equal to the combination of K, rho, and CP, the square root of all of them. So if we go and calculate F for the human flesh, it would be 1610. For the tiles, it would be 1425. For the carpet, it would be 249. And for the copper, it would be 37,136. Okay, so for the human flesh, F is equal to 1610. The initial temperature of the human flesh is 37 degrees Celsius. Plus FB, which is equal to the tiles, which is 1425, divided by 15, divided by F of the human flesh plus F of the tiles, is 1425, and if we calculate it, it is equal to 26.7 degrees Celsius. So this temperature between the human flesh and the tiles would be 27.6 degrees Celsius. And the heat flux is equal to Ka multiplied by Ts minus the initial temperature divided by the square root of pi multiplied by alpha A multiplied by T. You can also calculate it on the B side, on the tile side. Then it would be Ts minus the temperature of the tiles, but then you need to use the alpha of the tiles. Okay, Okay, and that is equal to K is equal to 0.623 multiplied by 26.5 minus 37 is equal to the square root of pi multiplied by alpha, and alpha is equal to K divided by rho Cp. It is our thermal diffusivity, equal to 0.623 divided by 996 multiplied by 4178 multiplied by, and let's calculate it after 5 seconds. So T is equal to, we want to know what it will be after 5 seconds. Okay, alpha, remember, is equal to K divided by rho Cp. Okay, and if we calculate the heat flux, it would be equal to 4.27 kilowatts per square meter. So it's 4,270 watts per square meter. 4.27. And if we now calculate the total heat transfer rate, it would be equal to 4.27, the heat flux, 4.27 e to the 3, multiplied by the surface area, which are for your 2 feet, are 2 multiplied by 0.020, and that would be equal to 170 watts. 170 watts. Okay, now except for the fact that we've put in some values and we've calculated everything, if we go back to what I've said the second observation is, and the second observation is that the body with the highest F value is going to dominate the temperature. Okay, so we can see the body with the highest F value is actually the human flesh in this case. Okay. It means that the temperature is going to be dominated by the human flesh, so it gives us 26.7 degrees Celsius. Go through, calculate the heat flux, and then the total heat transfer rate. We can now go and do the same, human flesh and the carpet. The human flesh and the carpet. We get onto the carpet, and now the surface temperature would be equal to, again, Fa, the human flesh, multiplied by the temperature of the human flesh, plus Fb, the Fb of the carpet, which is now equal to 249, plus 249 multiplied by 15, divided by the sum of the two F values, 1,610, plus 249, and that gives us a surface temperature of 34.1 degrees Celsius. So 34.1 degrees Celsius. Okay. So that is why it feels that when you get onto the carpet, that the carpet is warmer. But that's not the case. It is just the surface temperature between your feet and the carpet which is at a higher value, although the bodies are at the same value. Okay. If you go and calculate the heat flux, it is equal to 8.57 kilowatts per square meter. I'm not going to write it out. We've already done that. So let's put it in here. It is equal to, ladies and gentlemen, it is equal to 1.18. 1.18. And the total heat transfer rate is 47.2 watts. Okay. So in the first case, when you get onto the tile floor, 170 watts of your heat goes into the tiles. In the second case, when you get onto the carpet, it would be 47.2 watts of your heat going into the carpet. Let's look at the third one, the human flesh and the copper. The human flesh and the copper. In the case of the human flesh and the copper, the surface temperature is equal to the F of the body, which is still 1610, multiplied by the initial temperature of the body, which is 37, plus the F value of the copper, which is now equal to 37,136, multiplied by its temperature, which is 15, divided by the two F values, okay, and that gives us a temperature of 15.91 degrees Celsius. (15.91°C). So what we can see is that the F value of the copper is much larger than the F value of the human flesh, and therefore this body would dominate the temperature. Okay, so that is equal to 15.91, and if you go and calculate the heat flux, it's equal to 8.57, and that gives you 342 watts. 342 watts of your body heat that would go into the copper plate. Any questions, ladies and gentlemen?
So that QS will give you a negative value?
Yes, the QS is going to give you a negative value because of the temperature change. You just need to know it's a negative value, but normally we would ignore that because we know it is just because how we write the temperature difference. Okay. Any other questions? Okay. Now, let's suppose you say, well, let me go and jump into the pool. Okay. Let's go and jump into the pool. Okay. There you are before you jump into the pool. There you are in the pool. Let's also use the pool temperature as 15 degrees Celsius. 15 degrees Celsius, which is not that cold. Okay, it is cold, but I mean, it's not that cold. It's not like in the middle of winter. Okay, so remember again, if you are healthy, your temperature should be 37 degrees Celsius. Okay, now, if we look at the surface temperature is Fa multiplied by the initial temperature of body A plus F of body B multiplied by its initial temperature divided by Fa plus Fb. Now, because 72% of our body is water, okay, our thermal conductivity, our density, and our Cp values are very close to that of water. So for all practical purposes, Fa is equal to Fb, okay, which means that our surface temperature is going to be the average of the two initial temperatures, which is equal to 37 plus 15 divided by 2, which is equal to 26 degrees Celsius. 26 degrees Celsius. Okay. Now, if we look at this, we would say, oh, well, that is not so bad, is it? 26 degrees Celsius, your surface temperature jumping into the pool. But let's look at the heat flux. Let's look at the heat flux. Okay, the heat flux we can calculate as equal to K multiplied by Ts minus Ti divided by the square root of pi multiplied by alpha multiplied by T. And again, we are interested in the heat transfer after 5 seconds. After 5 seconds. So the thermal conductivity is equal to 0.623. The surface temperature is 26 minus 37. And yes, it is going to give us a negative heat flux, but we can ignore that in our answer. It's equal to the square root of pi multiplied by k, and I've calculated it. It is equal to 1.409 multiplied by 10 to the minus 7, and that is after 5 seconds. Okay. Remember, alpha is the thermal diffusivity. It is equal to K divided by the density multiplied by C. And that is equal to 4.605 kilowatts per square meter. 4.605. And if we look at these heat fluxes, it is not that high, is it? The difference, however, is the surface area. Previously, when you got out, on your 2 feet, it was 2 times 0.02 square meters. Now, the surface area is 2 square meters. So the total heat transfer rate is equal to 4.605 10 to the third multiplied by the surface, which is equal to 2, and that is equal to 9,211 watts. So it is equal to 9.2 kilowatts of heat going out of your body into the water. And that is why you get that feeling of, you can't breathe, because the massive amount of heat which is being transferred from your body to the water. Okay. Now the interesting thing is, in all the cases when we wanted the heat flux, we divide it by T. So when T is equal to 0, then our calculations can't calculate the heat flux. But after T equals 0, then we can. So if T was equal to 0.1 seconds, the heat flux most probably would go into the megawatts per square meter. An enormous amount of heat which is being transferred from you to the water. Okay. Right, ladies and gentlemen, any questions? If not, thank you very much.